unfortunately, 13 divides it by 199. Unfortunately, it's unluckily 13. The pun is intended. 13 divides it. 13 into 199 is so it's not a very good. Although there are other, I won't go into that. So each time I give a different lecture here in this festival, and so the talk this time is on global warming. Because last time I told economics because there was quite a bit. Actually, the budget is there, so maybe there may be a lot of discussions of it. So yeah, physics applied to economics, that was my title last time. And before that, it was on chemistry, because year of chemistry. And before that, Ramanujan thing that we had that golden ratio and Ramanujan numbers and all that. And then each time is a different topic. So maybe and whenever Professor Ramarao phones me in June, I know that this is going to be for this thing, and he won't take no for an answer. He won't take no for an answer, so I know it has to be an S, and he wants a topic also, and generally I give him straight away, without, because global warming is something much discussed, and so I won't, first of all, what is global warming, we'll see what does it signify, and I'll be talking more about the physics of it. There's much more politics to it than anything else, because there are a lot of, the first we started with the Kyoto Protocol, then it was Copenhagen, then Montreal, then Copenhagen, and goes on like that. And each time there is then Durban also in Africa. Okay, so each time there are all these, in fact in the last meeting Obama in fact gate crashed and made some statement about this. So anyway, we will focus more on the physics, what exactly is global warming, and is it really there, and what are the causes of it. So we'll go into that, so that will be the kind of thing. And what does it signify? So local conditions don't apply. For example, today, past few days Bangalore has been very cold compared to say a month back. So it was sweltering, You must say, what is this warming people are talking about? Getting cold here. And New York, had the worst winter in November, December. Okay, so everything had frozen completely. And and Moscow was very warm last October. So there are a lot of conflicts. So when we take global warming, we are talking about the average overall global as applied to the whole world, not local conditions. Because local, weather can change very much. Bangalore is very peculiar that way. You can have all the 4 seasons in one year. Okay. In a day, you can have all the 4 seasons. Okay. You can have rain also. It can be very warm. It can be very cold. So that is something very badly understood, and we hardly, there's a lot of things remaining to be understood. So, but one thing everyone agrees is global warming. Why does it? How does it play a role here? So, warning signs. So, in May 2012, it was documented that for the 327th consecutive month, global temperatures warmer than average. Okay. 327th consecutive month. Okay, it was warmer than average global temperatures, and chances of this are 1 in 10 to the 99. I've written work it out. So maybe, I don't know, any bright chem students here, immediately they can calculate. It won't take more than about 2-3 minutes. But not too many youngsters, right, attending these things. Anyway, maybe later on you can tell me the answer. Maybe many of the youngsters will prefer to go to the mall or have other better things to do than attend the festival. Okay. And so anyway, this is the... And in June 2012, so the hottest temperature in the US for several decades. Okay, this was also the kind of thing. And so in 2013, May, the CO2 levels first time they crossed 400 parts per million. Okay, 400 parts per million. I'll explain what is this 400 parts per million and why that is okay, and why that's considered very quite bad and dangerous. So melting of glaciers, see this has also been happening. Glaciers outside of Antarctica and Greenland lost an average of 260 billion tons of ice annually during from the years 2003 to 12, causing oceans to rise by 0.8 millimeter per year. This also something can work with the problem. See, in fact, we even thought of having a regular course in environmental physics. So all these things could be elaborated, but I don't think there will be many takers. First thing nowadays, people want to know whether they'll get jobs after the course. Not purely from the interest point of view. So this is another thing which can be worked out. So, okay, so this is one example of the, how the things are happening, melting of various glaciers and so on. Okay, so the another thing is the Great West Antarctic Ice Sheet. So it has got something like 3 million cubic kilometers. It melts, it melts completely. The ocean level will rise by 10 meters. Okay, so it is called WASTE, West Antarctic Ice Sheet. So it melts. It's actually a waste disposal problem to run on it. All coastal cities are inundated because many of the world's largest cities happen to be on the coast. Many of the world's largest cities happen to be on the coast. So it will create a real flooding problem if the ocean levels rise by some meters. So in fact, there's a book, Our Iceberg is Melting by John Porter. I don't know whether it's quite instructive that I hope the penguins are very worried about this. Okay. And the rate of melting of the ice sheets, icebergs for example, is a problem in physics. Suppose you got iceberg. Icebergs can be quite dangerous. They can be floating in the oceans. In fact, the Titanic episode would not have been there but for the iceberg. Okay, there was something to collide with. So all that's why icebergs can be floating around and could be quite dangerous. And water has a unique property that the solid is lighter than the liquid, that's why ice floats. Okay, and this is quite important from the point of view of the life on Earth because the ice is lighter, it floats. So the oceans don't freeze right, the seas don't freeze right through. So the life beneath the oceans is protected. Okay, so they don't die out. So this is quite important property of water. And of course, there are many other properties of water which are useful. For example, the high latent heat can show that all the oceans don't evaporate. You need about 540 kilocalories to evaporate 1 kilogram of water. Okay. But, you can't make tea instantly, right? You have to wait for it to boil, get water to boil. And so it takes a lot of energy to make water boil. That's why the oceans don't evaporate. Only small, just the right amount evaporates to have the regular monsoons, rain, and so on. Okay. And water has got the highest specific heat. Okay. Specific heat is the heat required to raise again, cool physics, 1 kilogram by 1 degree. And so water, if you have huge, luckily the earth is covered, 70% of the earth's surface is covered in water. So there are no extremes of temperature. Water takes a long time to cool and heat up. So if you see any weather map, or either on the TV or any other media, you see that there are no drastic differences in temperature between any two places. Maybe -10 to +30, not very big. Unlike the moon or Mars, the nights can be as cold as liquid air and daytime can be hotter than boiling water. Okay. So the water keeps the earth more or less comfortable in comfortable temperatures. That's why the earth is thriving. One of the reasons why the earth is thriving with life. Okay. So the rate of melting of the iceberg also is a problem in physics actually. Suppose you got a layer of ice on covering a lake or something about your water. Suppose the temperature drops to -10 degrees. How long will it take for the ice to become, say, 10 centimeters thick? 10 factors. It's a problem. I don't know whether these things are taught these days. So it's a balance between latent heat and and the heat lost or gained between the air and the surface of the water. So in terms of the diffusion problem, so that means the time taken goes to thickness square. Okay. So same thing applies to melting also. It takes a longer time because the layer is thicker to melt. So on. So this is the things. So towing of icebergs. So some people have the idea that you can tow icebergs. For example, there was a conference because the Middle East has got a lot of water problems. They are rich in oil but poor in water. Okay. Water is also important. Okay. And what they can do with oil, they can only export it because what else do they do with oil? Right? They can use it to see all the colleagues and they have to do with this funky, all the fast-paced cars and vehicles, even aircraft. But you see, they can't use more oil than what is. There are a lot of it is left over, so they can sell it. But water is a serious problem there. Okay. And in fact, water is anticipated in a few decades. Also in Bangalore it is there. Okay. So many TMCs of water and so on. Okay. And so that's a serious problem. In fact, there could be water wars also after some decades, like oil wars. So one of the ideas was, there was apparently a conference, they suggested that you can tow an iceberg from the Antarctic to one of these sufficiently big iceberg. You can tow it, it can supply water to Saudi Arabia or one of the countries for quite some time. Okay. But it turns out that if you do the problem, if you tow it with a rope, it turns out once it crosses the equator, only the rope is left. so that's again a problem. So it was abandoned. Okay. So the thing is, all ideas need to be quantified. That's where physics comes in. So if somebody gives you some crazy idea or some wild idea, you have to first see whether it is viable, you have to work out, put parameters. So that's again, that's why physics, is everywhere useful. Whatever area you choose to apply it to, okay. The technology or biology or whatever. Okay. And of course, global warming. So there are many reasons why we think global warming. So many of these reasons. The Arctic considerably, Arctic has changed completely. Many of the glaciers have melted and so on. So many things which are earlier frozen are now accessible. Ships can move on. Polar bears are worried, their habitats have decreased and so on. There are a lot of reasons. And in fact, in Britain, France has a lot of vineyards. French and Italy, the southern part of Europe, they make very good wines. But England never used to have good vineyards because it's too cold. Okay. But now vineyards are improving in Britain, and there are many more vineyards in Britain now, okay, than before. There's another, so there are good effects of global warming out there. Okay, even Britain may not import from countries with below like France. Okay, so that's one. So this is all called what's called greenhouse effect. We'll come to that later. And CO2 is blamed normally. It's a major culprit. You'll see later it's not the only one. Although, see, they have to find some scapegoat. CO2 is the main scapegoat. Okay. But it cannot be the only one. And why is CO2 blamed? We'll come to that next. What is greenhouse effect? First of all, this is something in physics. I think many of the audience, many of the people in the audience might have had a course in physics or maybe physics. So anyway, just for completion, I explain what is greenhouse effect. So, how does it warm the Earth? Now, Earth receives radiation from the sun about 1 kilowatt per meter square. Okay, maybe it is somewhat more on certain places. The average is 1 kilowatt per meter square, and total is 3 into 10 to the 17 watts. The whole Earth gets something like 0.3 exawatts from the sun, mostly visible and infrared. Okay, to a much small extent. So the sun's surface temperature is such. Again, we apply the laws of physics, Green's law, and so on. So much of the radiation is in the visible part of the spectrum. Okay. So the radiation from the Earth, of course, has to go back into space. Okay, law of thermodynamics tells you the Earth should also radiate back into space what it gets. And the radiation from the Earth back into space depends on the temperature of the Earth. Okay, depends on what temperature the Earth is. So say about 300 degrees Kelvin, it will be mostly in the infrared. It will be radiated back in the infrared. And so it will be mainly in the infrared part of the spectrum. While the air is transparent at ordinary visible wavelengths, the air is transparent, otherwise you won't be able to see the stars and sun. Air is obviously transparent and visible thing, but need not be transparent at the infrared. Okay, so that's where the problem comes. Except of course the smog. With the smog, of course, you can't see, visible light also can't propagate. That's why aircraft cannot land, traffic will be affected. But the smog is a combination of smoke and fog. Okay. In case you're wondering how the word comes, is what's called one of the portmanteau words. That is, you combine two words to get that kind of thing. So smoke and fog give you smog. So whenever the smog, the visibility is lost. Okay, you can hardly. So there visible light is available. Otherwise, clear air will allow visible wavelengths to freely penetrate. Okay. Now you have got this. 6% scattered from the atmosphere, 19% absorbed by atmosphere and clouds, 4% reflected by the surface, 51% absorbed by the earth, 20% scattered and reflected by clouds. So there are so many things affecting how the sunlight propagates. Okay. So this is where the physics comes in. So we have to put a balance between all these things, and of course this is not a course, so we won't elaborate on how these things are calculated, but you can get an idea of what happens to sunlight received by the earth. So it's not transparent in the infrared part of the spectrum. Okay, so it turns out the atmosphere is not transparent in the infrared. What does it mean? So when the Earth likes to radiate into space, that is the radius in infrared, some of the gases in the air, okay, in front of us, okay. So CO2, water vapor, methane. Why are cloudy nights? See, cloudy nights are quite warm, sultry. The night is cloudy. This is a common observation. What's happening? Water vapor doesn't allow the infrared radiation to go into space. It traps it. So water vapor is an example of a greenhouse gas. Okay. So that's quite a common observation. So it turns out apart from water vapor, there's also CO2, methane, all these other gases are there. Okay. So cloudy nights especially, there's a common one. This is one example of a greenhouse effect. So it happens to absorb strongly in the infrared. Okay. These greenhouse gases happen to absorb strongly in the infrared, although they are transparent in the visible. Okay. So they let in sunlight, but they trap it and prevent it from getting out. They prevent it from getting out. And the infrared radiation thus warming up all that's inside. So all that's inside gets warmer because the radiation cannot escape from this trap. So it has to make it warmer. And warmth is nothing but infrared radiation. That's what you know, when you say something warm, you mean in the infrared part of the spectrum. So radiation, infrared radiation thus warms up all that's inside. In fact, glass also plays a similar role. Glass house also is warm. Inside of a glass house is warmer than outside. Just like people inside glass house should not exhaust smoke. Okay, this is the glass house effect. So similar to the greenhouse effect, glass also plays a similar, although not in the same, quite in the same wavelength, but the effect is similar. Okay. Absorption by these gases is due to the vibration transition. For example, why does this kind of thing occur? Because CO2, the carbon dioxide, has a vibration absorption of 15 microns. Okay. So, and vibration overtones of methane is at 3 point. This is the little details of the physics. You don't have to worry much about it. So, if you actually want to understand in detail what exactly is happening, these things are important. So, you've got a pure rotation spectrum like water vapor at 20 microns. So, that's why all the infrared radiation is tracked, because these transitions take place in these molecules. And as the mean peak of the Earth's thermal emission is 10 microns. Okay. Any black body spectrum has got a peak, and it turns out for the Earth's temperature is about 10 microns. Okay, that's what happens. And so these gases can give much opacity. Why are they opaque? When you say something is opaque, radiation cannot get out. Okay, it's transparent, radiation goes very far. So these gases make the sunlight opaque, the infrared part of the spectrum, and the opacity depends on the wavelength. Okay, something may be transparent to visible, but may be opaque to infrared. Something may be transparent to X-rays, but opaque to something else. So it depends very much on the wavelength, because refracting index depends on the wavelength. So that's why. So this is where the physics comes in. It's a wavelength dependent thing. So these gases can give much opacity. So if you put a layer of these gases above the Earth's surface, sunlight would get in but not get out. Okay. So when the surface tries to radiate back in space, what is happening is impeded. The path is impeded by the blanket of infrared absorbing gas. So you have a blanket of infrared absorbing gases. These are called greenhouse gases. CO2, water vapor, methane, all of them. They prevent the heat from getting outside and warm up the Earth. Okay, that's what happens. Okay. So the Earth warms up to achieve equilibrium with sunlight coming in and exiting. In limited amounts, is anything limited is useful. Any phenomena which doesn't occur in extremes is useful. In fact, for example, I told you cloudy nights are warm, so it's good in a way, because otherwise it will feel colder. Okay, so it has got some benefits. Gas has got some benefits. It gives the temperature, the Earth's temperature, a higher value than what it normally have if the just sunlight is hitting the Earth and nothing else. Okay. So that's what happens. That's why the surface of the moon is much hotter than the Earth, because there is no atmosphere. Okay. So the surface of the moon is much hotter. Okay. That's what happens. So the Earth warms up to achieve equilibrium. And a little greenhouse effect is a good thing, okay, but it avoids extreme cold. So there's a delicate balance of gases. However, if you keep adding more and more such gases, mainly CO2. Why CO2? Because CO2, we see much of our power, we see later comes from burning fossil fuel like coal. Okay, we have been doing that since the industrial revolution. Industrial revolution ushered in the so-called technological age. And machines became widespread, use of machinery became widespread. But you need power for all these things. Okay, you can't run with. See, you have manual labor, you got power from your muscles. It comes from the food you eat. But you got these machines. You need something to power them, and you need power like thermal power, or electric power, and so on. So the fundamental thing is the thermal power, the coal much of the power came from fossil fuels, even now it is so, from coal and oil and so on, and they all produce CO2 as a byproduct. So we have been doing this since the Industrial Revolution, which started around mid-19th century. Okay. So you can make the blanket thicker and thicker, absorb more and more infrared, because the CO2 hangs around. Okay. It doesn't matter where it's produced, it hangs around in the air. It is there for quite some time, several years. So the blanket becomes thicker and thicker. That's what happens. So make the earth warmer by trapping in more and more heat. So you see this thing here, I'm too hot, no more blankets. It keeps on getting. So you can't keep on piling blankets, even if the weather is extremely cold. You keep piling more blankets, you start feeling warm. Okay. So that's what happens. So how much CO2 are we adding? Next question, how much CO2 are we adding? So what quantity, what does it mean? I told you for the first time it crossed 4,000 parts per million. Okay, they have calculated. They have sort of actually measured and found. How does it happen? So our atmosphere is mainly nitrogen and oxygen. Any school textbook will tell you. Okay, 78% nitrogen, 21% oxygen, and so on. Okay, and the CO2 is quite rare. It's only 330 parts per million. ppm means parts per million, and that means of course there's one gas which many people do not know this. Many textbooks don't mention this. There's one gas which is much more abundant than carbon dioxide in the atmosphere. The argon. Argon constitutes 1%. Okay. And that's how it was first produced. See, people did not know what argon. It's an inert gas. In fact, that's how Lord Rayleigh first deduced there must be some heavier gas in the atmosphere. Because he found, see, nitrogen you can make in the laboratory also from chemical reactions. He found the nitrogen in the laboratory weighs less than the nitrogen in the atmosphere for the same volume. So he said, why is atmospheric nitrogen heavier than the laboratory nitrogen? So he concluded there must be some gas there which is not playing